Ever wondered how industries like healthcare, energy, finance, logistics, and aerospace navigate their unique challenges? Let's take a moment to explore this fascinating topic. Each of these sectors is faced with a unique set of problems. For instance, the healthcare industry grapples with disease prediction and drug discovery, while the energy sector is constantly looking for efficient ways to manage power grids. The finance industry, on the other hand, is always in search of more precise risk assessment models, and logistics is all about optimizing routes and schedules. As for aerospace, well, the challenges are literally out of this world, from spacecraft design to trajectory optimization. Now, wouldn't it be wonderful if there was a method to address these challenges in a precise, efficient, and innovative manner? Well, enter the world of quantum computational modeling. This revolutionary approach aims to provide industry-specific solutions by harnessing the power of quantum physics. Imagine a world where we could predict the efficacy of a drug before it hits the market, or manage energy grids with near-perfect efficiency. Envision a financial market that can accurately predict risk, a logistics network that is always optimal, and spacecraft that are designed with unparalleled precision. With quantum computational modeling, these are not just fantasies, but potential realities. You might wonder, how does this all work? Well, it's all about equations. One such equation is the McGinty equation. This mathematical model, with its intricate combination of quantum field theory and fractal geometry, allows us to simulate and solve complex problems in a way that traditional computational methods simply cannot. The McGinty equation may sound daunting, but its potential is immense. It represents a bridge, a way for us to translate the abstract world of quantum physics into practical solutions for real-world problems. What if we told you the solution to these complex problems lies in the realm of quantum physics? The McGinty equation, appearing complex at first glance, holds the key to understanding quantum computational modeling. It's a mouthful, isn't it? But let's break it down. First off, PESQFTXT is the solution to the free quantum field theory. Think of it as the basic quantum state, a starting point, if you will. It's the foundation upon which everything else is built, the blank canvas where the magic of quantum computation begins. Next, we have bisfractal XTDMQS. This term represents a fractal structure, a pattern that repeats itself at every scale. You've probably seen fractals in nature, the spirals of a pine cone, the branches of a tree, even the veins in your hand. In the McGinty equation, the fractal term introduces a self-similar pattern into the quantum field. It's a bit like adding a recurring theme to a symphony, giving the piece a sense of unity and harmony. Now let's talk about the modified McGinty equation. In this version, we have an additional term, gravity, XTG. This term represents the perturbative effects of gravity on the quantum field. In simpler words, it accounts for how gravity tugs and pulls at the quantum field, like the moon's gravitational pull causing the tides on Earth. The G in this term is a parameter that characterizes the strength of the gravitational force. It's the knob we can turn to tweak how much gravity affects our quantum system. Finally, the fractal potential term VOIT has a self-similar fractal structure, described by the constant parameters V0, L, and S. This term can be derived using integral calculus, Laplace transform, and the convolution theorem. It's a bit like the secret sauce that brings all the flavors together, adding depth and complexity to our quantum computational model. So there you have it. The McGinty equation, once decoded, becomes a powerful tool in quantum computational modeling. It's a bit like a multi-dimensional jigsaw puzzle. Each piece, each term, has its place and role, and when they all come together, they form a complete, coherent picture of the quantum world. Now that we've decoded the McGinty equation, let's delve into the potential of quantum computational modeling in various industries. Imagine a world where healthcare is personalized to a molecular level, where patients receive treatments designed specifically for their unique genetic makeup. This isn't a distant dream, but a reality that quantum computational modeling can bring to life. With the McGinty equation, we can simulate complex biological systems, enabling us to better understand diseases and develop targeted treatments. In the energy sector, the equation's self-similar fractal structure can be used to simulate and optimize complex energy systems. This could lead to more efficient power grids, renewable energy sources, and even a path towards sustainable nuclear fusion. Finance, too, stands to gain immensely. Quantum models can tackle the complex, dynamic nature of financial markets, They will enable risk assessment and asset valuation at an unprecedented level of accuracy, helping investors make informed decisions. Now consider logistics. The global supply chain is a labyrinth of interdependent nodes. Quantum modeling, using the modified McGinty equation, can optimize these networks, saving time and resources, and ensuring smooth operations. And let's not forget aerospace. The perturbative effects of gravity on the quantum field, as represented in the equation, can help us understand and navigate the cosmos better. It could lead to breakthroughs in space exploration, satellite technology, and even interstellar travel. All these scenarios are not mere conjectures, but tangible possibilities that quantum computational modeling, underpinned by the McGinty equation, can manifest. It's a tool that can address the unique challenges of different industries, providing solutions tailored to their specific needs. The beauty of the McGinty equation lies in its adaptability. Whether it's the free quantum field theory, the fractal potential term, or the gravitational effects, each component can be tweaked to suit a particular context, giving us the power to shape our future. Quantum computational modeling, powered by the McGinty equation, is poised to revolutionize industries. So we've journeyed through the complexities of the McGinty equation and explored the potential of quantum computational modeling. But what does this all mean for our industries? Let's take a step back and connect the dots. Quantum computational modeling is a game changer for industry-specific challenges. It paves the way for tailored solutions, each uniquely designed to address the needs of different sectors like healthcare, energy systems, finance, logistics, and aerospace. With the power of quantum mechanics, we can delve into the heart of complex problems and unlock innovative solutions, far beyond the reach of conventional methods. Imagine the future of healthcare with personalized medicine, or the energy sector optimizing renewable resources, all thanks to quantum computational modeling. We're talking about a revolution in how we approach problem solving. And remember, this isn't just a fanciful idea or a distant dream. Quantum computational modeling is not just a theory, it's the future, and it's happening now.